All right, I'll start the recording then. So welcome back officially, Roomers, Zoomers, and folks listening at home. I've got, let's see, I updated grades this morning. Thank you for everyone getting your homework done on time. I was so impressed because that is the hardest assignment of the year. It's downhill from here. The last assignment will have no drop-down results questions, only multiple choice questions about path analysis. And it will be one model because getting that one model right will be enough. If you have not gotten both points for your homework 5 plan, that means that I need more information from you, and so that we can settle on what you're planning on doing. There's a couple of you who need to provide me with a response. So you can email your document back to me. The feedback is available inside the homework portal. That's where those are, which is why I asked you to name your files in a particular way, so it generates dynamic links. That way everyone can download their document. If you can't access your document or you're otherwise have questions about my feedback, please let me know. So next thing up is formative assessment number 5, I think. We're up to number 5 by now. That's due Monday night. That's over the things we're talking about this week. And then a week from Monday is your homework 5 individual data analyses. So lots of different topics, and I'm looking forward to seeing what you come up with. So that's always fun for me to see what people are working on. I think that's all the logistical stuff I wanted to mention. Any questions about assignments, requirements, process, any of that stuff? No? Fair enough. Then what are we talking about this week? What do you remember from Garbage Day? As usual, I will take gestures, words, phrases, letters, numbers, punctuation marks. Multivariate. Yeah, what does multivariate mean? Yes, so this is actually, that word has different definitions based on who you talk to. Some people think that an analysis that involves more than 2 variables qualifies as multivariate. To me, that is not the right label for it. If you have multiple predictors, I might call it multivariable, but multivariate means multiple outcomes. So when you have multiple outcomes for the same sampling unit, usually person, but it could be other things as well, then we need to adapt our models to be able to address what's the big concern if you have multiple outcomes from the same person. Starts with a D. Yeah, what does dependency mean? In a word. Thinking of one word, starts with a C. Yeah, correlation. Yeah, correlated residuals. I'll take 2 words for that. What were you have different words?
I said the wrong word.
Is it wrong or is it just different?
Collinearity?
You know, it's related. So collinearity would be like relationships among predictors, but it's the same idea, just among the residuals. So I'll take it. Yeah, the idea that the typical assumptions that we make of independent residuals are not likely to hold if we have multiple outcomes from the same sampling unit, so we got to adjust our model. So that is true regardless of whether we have models predicting continuous or continue-ish outcomes, or whether we have generalized models. So everything we talked about up to this point is for single-level samples with no dependency, and so we're sort of changing gears into extensions for dependent samples. Let's see, we're going to talk about, in terms of sampling designs, balanced versus unbalanced. Do you remember that from last time? Should we review this a little bit? That'd be good. This is a quiz question. So I want to be upfront about what we're going to cover and what we're not going to cover. So my definition of these words, again, people use the same words to mean different things. A balanced sampling design from the perspective of multivariate observations is when there are the same possibilities for everyone. So like there's only, so many occasions, so many conditions, so many types of outcomes that you're collecting multivariately. It doesn't necessarily mean that you have complete data. So you might have like wave 1 and everybody was measured on the same day. You come back 6 months later, wave 2, everybody's measured on the same day. Maybe you don't have wave 2 for everybody, but there's only like 2 possibilities. Pre-test, post-test designs would fall into this category. I will tell you though, as an aside, if you're interested in measuring change over time, pre-test, post-test is not a good idea. You need at least 3 occasions to be able to differentiate individual differences in change from measurement error. And pretest, post-test does not give that to you. But that would be an example of a balanced design where everybody has a pretest and everybody has a post-test, and there's not multiple kinds. Unbalanced would be, for instance, if we think about classrooms as the sampling unit that's being measured repeatedly by multiple children, and not every classroom has the same number of kids. So you might have kid 1, kid 2, kid 3. Some classrooms have 30, some classrooms have 20. That would be considered unbalanced. Likewise, if you have a longitudinal study, so the intensive longitudinal data or ecological momentary assessments, as they're called, like where you have like an app on your phone and it beeps you every so often and you tell it, what's my negative affect, what's my stress level, and those kinds of studies, those would be unbalanced because the beeps are coming at random intervals. So when you get beeped is an individual specific and day specific occurrence. It's not like you have a morning, an afternoon, and a night where it's exactly the same times for everybody. So in this unit, we're talking about balanced, where there's a finite set of possibilities. And the big difference in terms of balanced versus unbalanced is a distinction that shows up in the upper level courses on multi-level models. So the clustered multi-level class is coming back in the fall. Longitudinal will come back as a 2-semester sequence the following year. So questions or comments about that? Balanced versus unbalanced? Good so far? No? All right. In terms of what differentiates the approach that, thank you for the thumbs, Zoomers. In terms of what differentiates the approach that I'm taking versus what, say, like the multivariate class would cover, is the use of likelihood estimation. So there's nothing wrong, say, with MANOVA as an analysis. It's looking at group differences and multiple outcomes simultaneously. Where the problem comes in is the use of least squares estimation, so sums of squares stuff where we're dividing up things into sums of squares model and sums of squares group and sums of squares residual and all that stuff. In order to have a sum, you have to have complete data. So list-wise deletion is a consequence of least squares estimation, ordinary least squares in particular. By switching to likelihood estimation, then we are allowed to keep observations that don't have all the outcomes, which is better not only from a perspective of power, but also in terms of inference. So like if you have a pretest post-test design, you probably learned in intro stat about a dependent samples t-test, right? Like you can just look at the difference before and after, and you can do a t-test on it, and that's your answer. But a t-test is a least squares type of idea. So you are only allowed to look at differences for people who have both the pretest and the post-test. But what if people don't come back for reasons, right? Like usually attrition is not a random selection. There's a reason people don't come back. So by limiting your analysis to completers, you're changing the population that you can talk about. It's like amongst the conscientious completers, this is what happened, not amongst all the people that I potentially want to talk about in terms of my inference. So likelihood estimation is what makes sort of the approach that I'm taking, I think, different than what you may see in sort of older approaches that use least squares. Yeah, so we're going to look at tricking software that is meant for univariate analysis into doing multivariate models first, and then transitioning into path analysis. So the difference, by the way, between structural equation models and path analysis models lies in the use of latent variables. Path analysis is looking at relationships among multiple observed variables only, whereas structural equation models adds latent variables into the mix, in which that typical purpose of doing that is to build a measurement model to identify a construct via multiple measures that should be more reliable than any one measure would be in and of itself. So that's a whole different class, but in terms of the terminology, I just want you to be familiar with those terms. All right, does that sound familiar? I think my caffeine just hit me. Sorry, I'm like, ah! Questions so far? No, we're good? All right, cool. Moving right along then. So 2 ways then in multivariate analyses that we can introduce residual correlation into the model. So rather than saying, well, they have to be independent, we'll say, no, they can be dependent with a particular pattern to it. You can do so directly by simply letting residuals have covariances. So you can just tell the model, I'd like the residuals from the same people to have this correlation pattern, and it's like, okay, here you go. Indirectly is the alternative. Indirectly uses random effects. So is this a term that you've heard before? Yes, in what context have you heard random effects so far? Yeah, that is opposed to fixed effects, that's true.
I think it was at like the very end of our general linear models class, like the last week or something, it was like thrown out there as this thing that you can do, and that was that's all that I got out of it.
Mhm.
To that professor's credit, there was probably more.
Well, yeah, I mean, if it's like the last week and it's only 1 week, then thing you can do is about all you can get through in 1 week. I will agree with that assessment. But yes, that is the reason why when I teach regression, I call the slopes and intercepts fixed effects from day one, because I'm setting up the idea that there's more than one kind of effect. There are random as an alternative. Fixed effects are estimated constants. So like if I have a slope that's 2, that 2 applies equally to everybody. A random effect is a variable. Each person gets their own version of it, and rather than estimating what that is per person, we estimate the variance across people. So random effects and random intercepts in particular is really your only choice when it comes to generalized models for introducing residual correlation. So we'll talk a little bit about that, and I'll show you some examples. This is also more generalizable to unbalanced situations. So adding a random intercept, for instance. Do you remember repeated measures ANOVA? Did you learn about that in your intro classes? Maybe a little bit, or a week on it? Yeah, you did, for sure, right? Yeah. In psychology, it's like, no, this is repeated measures ANOVA is where it's at. So when I learned repeated measures ANOVA, the way that I learned it is, in contrast to regular ANOVA, there's this extra hold each person like their own constant person differences, and we kick that amount of variability out of the error term, and then our tests of our manipulation get stronger. Well, the thing we kicked out of the error term, that was how I learned it, that's a random intercept variance. So random effects essentially involve taking the total variability in your outcome and separating it into different parts. How much of it is in common across the outcomes from the same people, and how much of it is outcome specific. So it generalizes to more situations. It's just an indirect way of building in correlation. So I'll talk a little bit about that, but if you really want to get good at it, that's where the world of multi-level models comes in. Mixed effects models is a synonym for that, by the way. Mixed effects means a model has both fixed effects, which is the default, and random effects at the same time. You would never have a random effect without a fixed effect, though. There's a hierarchy. So fixed comes first. You can also add random over it if you want to. What ends up happening is that the fixed effect is the center of that distribution of the random effect variable. So like the 2 would be what happens on average, but each person can get their own version of that 2. So we'll get there. All right, so we started looking at a little bit of notation to try and describe how these models look different under the hood relative to models for independent data. So a simple example here. If I write this model in what I call scalar form, this is the way that I tend to approach it because it's the most transparent. I tend to avoid matrix representations because just looking at x beta here doesn't tell you what's in the model. I don't know from this how many x's I have and how many betas go with it. But in terms of the matrix representation, E here is a column of residuals, and what's happening under the hood is that we're building a giant covariance matrix of these E's across people, in which we say that the E variance is the same across all people. So this is 6 rows, 6 columns for 6 people. And the zeros here indicate that the E's are supposed to be independent. So like this is what's being built for you when you run a linear regression. These are the default assumptions. So this type of format is called type VC in SAS, stands for variance components. In Stata, this is an independent covariance structure. That's the key word. And the zeros here represent the idea that people should have independent residuals after you control for whatever fixed effects. So the idea that each person has one outcome, we can decide what type of outcome that is in terms of what kind of conditional distribution and compute a height for how tall that person's outcome is given that distribution formula, such as univariate normal here. So each person has one y, and as long as I know what the predicted y is for that person based on my fixed effects, and I know the residual variance, I can plug those numbers in here and I get a number back. We have the height of the one observation. To combine these heights across people, we take the natural log of the height, so we're changing it from likelihood into log likelihood, and then we can add them together. The only reason that is allowed, though, is because of this assumption of independence. Otherwise, we can't directly add them, or we couldn't directly multiply the likelihoods. But what if, as we talked about at the end of class, like the first three outcomes here all came from the same person? Well, then trying to figure out what the height is independently isn't going to make as much sense as trying to think about the collection of a set of outcomes for a person being the unit of analysis. So like, what's the height of the three jointly is where we're headed with this. So here's how we can trick software that is meant for one outcome at a time into doing multivariate analysis. We're changing the data structure. So over here, these are words, by the way, that are almost universal. And so I want, this is something that to commit to memory, wide versus long data structure for multivariate analysis. So a wide, or what I refer to as multivariate, meaning multiple outcome columns, looks like this, where it's one row per person, and the multiple outcomes that you would have for each person would be in separate columns. So if I have two outcomes per person, let's say I have time 1, time 2, then I would have two different columns. The question is then, how do I get an analysis where I can predict both of them at the same time? Because if I want to do like a pre-test, post-test, I have to have both of these in the model so that I can have the difference. It requires restructuring the data set. It's known as reshaping. I also call this stacking, to go from a wide format like this to a long format. So if you, visually, it's like you're taking each row and transposing it row by row, like that. So then we have one row per outcome per person. So in this example, because each person has two outcomes, in the long data structure, they have two rows of data. So whatever is constant to a person, such as their ID number, such as anything that was collected once, would be pasted down for all the rows of that person, and that's important. It has to be that way. It's not redundant. If you only had like the person information on one row, all the rest of the rows would get kicked out of the analysis. We then build a new type of ID variable that keeps track of which outcome it is. So at a minimum, I need something called time here. In more complex designs, I might need more than one of these. So I've got what used to be contained in the names is now contained in the values of this time column. If I wanted to put time into the model then as a predictor, then that effective time would give me the difference between pre-test and post-test. But if I put time directly in as 1 and 2, who is my intercept for? Or when would my intercept for? When would my intercept be for? There we go. That's a sentence. If I put in time 1, 2 as my predictor, when would time 0 be? Like before pretest. Like it's not wrong, but it's weird. So for the same reasons that we want to have a meaningful intercept as our expected outcome for the reference type of person or the reference occasion, I would change this into a column that's centered. It'd be 0, 1 instead. And then now, I have one column that according to the software is just y, because it's the same type of variable, but it knows from which original column it came because of these new middle columns here as the ID variables. So every software package on Earth has the capacity to do this for you in like 4 lines of code. I have had graduate students try to do this manually in Excel. Please don't ever try to do that. It's a recipe for disaster. I didn't know all of the capabilities of this when I was a graduate student either. I once had a data set that looked like this, and what I wanted to do was get the mean for the outcome across all the rows for the same person. And I spent 6 weeks running separate analyses for people to get that mean, literally, and then I was entering those means into another data set, and then like 4 years later, I realized that that was an aggregate command in SPSS, and in one line of code, it would have done it for me. So yeah, this is one specific example, but in general, if you're ever faced with a data management where you find yourself having to do the same thing over and over again, but just changing like one piece of it, that probably can be done by software faster and better. I'm happy to help you troubleshoot those sorts of problems, like here's what I'm trying to do, how can I do this more efficiently? Because I've encountered a number of these problems in practice before. So this idea of reshaping, this would be called wide to long. To go backwards would be long to wide. When you're entering data to begin with, long is better. Long is always better. Because then you can have multiple columns that keep track of whatever piece of information you need to know about each outcome, but you can always flip it back to wide if you need to, or aggregate to whatever level of analysis you would need to make sense. So we have to get to the point in order to use univariate software where y is one column. And this is what you would do, for instance, if you did want to do a repeated measures ANOVA using likelihood-based estimation, whereas traditional repeated measure ANOVA uses this wide format over here instead. All right, how are we doing? Cool? Good enough? All right. Thumbs, I like thumbs. Any questions, Zoomers? All right, so now that we have all my y's stacked into the same column, what if I had the same 6 pieces of data, but now it is 2 occasions each from 3 people? So I'm changing the notation to accommodate this idea. And this is actually backwards from how I do it in the multi-level classes, because the way that I'm thinking about it is multivariate instead. So I have yit rather than y sub I, because y is looping over both people and time points. So I have to know for which person this y is and for which occasion this y is, so that is it. Because I have 2 subscripts on my outcome variable, my fixed effects now have 2 subscripts as well. So the first subscript would go with person predictors. So 0, 0 would be the starting point of beta 0 for the intercept, same idea. The second subscript would keep track of which time predictor it is. So the effect of x here as time 0 versus 1 is beta 01, because this is the first predictor at the time level. If you had more than 1, then it would be 02, 03, and so forth. Likewise, because we have a separate y for each person in each occasion, I have a separate e for each person in each occasion. Subscripts are always author specific. You are not required to use IJK though. You will see that in all the papers. Do not do it, because then your reader has to be like, what's J again? What's K again? Like if I were doing, kids in schools, I'd go KS. Seriously, like if I were doing, clients and businesses, I'd say CB. Like you are allowed to use whatever letters you want. And if you make the letters match the idea, then the working memory load it takes to track the equations is significantly less. So I for individual, T for time is the idea here. Time as my multivariate observation. So then per person, I'm picking up I subscripts on some of my matrices here, the Y, the X, which is the predictors, and the E. Per person, I have 2 occasions. So then my collection of E residual variances and covariances would have this type of structure instead. So previously, we had the same residual variance all the way across the diagonal because it was one type of outcome across 6 people, and we had zeros everywhere. Now I'm making a distinction for what the residual variance would be for time 1 versus time 2, so they could be different. That's a choice. Odds are good that if you have a pretest post-test and people change differently from pretest, that means you're going to have more variance at post-test, because if people change differently, they spread out. It's an empirical question whether you should constrain the variability that's left over in your first outcome to be equal to your second outcome. Then this piece right here, this is a covariance. We will tell the software, hey, take the e's from the same person and let them have a covariance. And we can convert this into a correlation if we want to as well. So then this little idea of this 2 by 2 in little sections like this is what's known as a block diagonal. So the data from the same person are within these blue blocks, and data from different people are the zeros otherwise. So the model is allowing dependency only between the outcomes that come from the same person. People are still independent. But this foreshadows, what would I do if this were a clustered sample, where, say, this person and this person were from the same classroom, but this person was from a different classroom? Well, I need something over here that would allow the people from the same classroom to be related. Random effects are one way to do that, to build in extra patterns of correlation for people who come from the same clustering unit. So the name of this thing is an R matrix. The correlation version is R core in the notation that I'm using. So you'll see those words in the code because you can ask for these types of predictions as part of your output as to what is the pattern of variance and covariance across your multivariate outcomes according to the model. The fact that I have the same 3 symbols in every single block here is conveying the idea of homogeneity of variance. Like the same variance terms apply to all the people. It's not that some people have more variance at pretest than others. That's also a choice. That's not something you can easily add in the world of ANOVA, but it is if you're switching to likelihood estimation. Okay, so this is the new piece here, being able to tell your software that you want residuals from the same person to be correlated, as well as to allow different variances for the 2 different types of outcomes. So how do we do that? We change our definition of height. We need a multivariate distribution rather than a univariate distribution. Here's some pictures that I stole a long time ago, so I don't remember where I stole them from. But the idea of no relationship between 2 variables, x and y, in a multivariate distribution would look like a sphere. And this taco-looking thing would convey a negative relationship. If it were a positive relationship, it'd be a taco going the other way. So we're still at the idea of height. It's just height in multiple dimensions at the same time. Here's what the formula for height looks like. It's a little uglier. We have to switch to matrices because we're talking about building predictions for a set of outcomes rather than a single outcome, but otherwise it follows fairly directly. So in the univariate formula for height, we have my sigma squared E thing here. What's that? Do a little review, because this is from like January. Yeah, error. Residual variance in general linear models. Have we seen this in the last 3 months since then? We have not. Generalized models don't have this. In the binomial distribution, the mean is a function of the variance. In the Bernoulli distribution, the mean is a function of the variance. In Poisson, the mean and the variance are the same number. You can add in a stretchy over-dispersion to make it negative binomial. You can add in an over-dispersion to do beta binomial and something analogous to that in gamma, but normal is the only distribution we've seen that has a separate estimated variance. Well, this is a variance because we had an outcome. So that has to become an R matrix in multivariate settings. And this R here refers to this little block diagonal. So the 2 by 2 thing, because we have 2 outcomes. That's what that refers to. In this case, the bars around it are specifically referring to the determinant of R, which is a matrix term. So if you take the multivariate class in the fall with Steve Dunbar, he will talk about determinants and things like that of matrices. An easy way to think about it is that it's the amount of information that's not redundant. You can end up with estimation difficulties if this thing gets close to 0, because you end up having to divide by it. In matrix terms, it's like division, but it's an inverse. And so you may get error messages that say something like, I had singularity, I used a generalized inverse. That's referring to this basically having not enough unique information to make the analysis go. So we have my R matrix replacing my residual variance. Rather than having The difference between the y that I have and the y that's predicted, I have the same idea captured in matrices here. I have my r showing back up over here again, and then note that beta does not have an I subscript on it because beta is your matrix of fixed effects and they apply to everybody. They're not individual specific. Everything else potentially is. So if I am supposed to have 2 outcomes and I have 2 outcomes, then my individual r is a 2 by 2. If I am supposed to have 2 outcomes and I only have 1, then my r is a 1 by 1. So it adapts the number of dimensions to whatever a typical person has. At the end of this whole process, though, it's the same idea. You get a number. You get a number that summarizes the height of your set of outcomes together, given the current values of the model parameters. And the process of estimation tries to figure out what model parameters collectively make the height the biggest for your sample. And that combined height, if you take the log across separate people and add it together, that's your log likelihood. So it's the same set of ideas that we had in univariate, just for multiple outcomes at the same time. We change the definition of height according to what conditional distribution we have. So if you have a binary outcome, then you would have a Bernoulli-based height formula for univariate. There are multivariate Bernoulli distributions, for instance, and so on. So height is a distribution-specific concept. We're just changing it to have multiple dimensions in the same time. And no, I don't really expect you to remember any of this. Just the idea is collectively, height across all sets of outcomes. That's what we're changing it to. What about missing data? So I got some good news and I got some bad news. In repeated measures ANOVA, if you're using least squares estimation, it will drop anybody who's missing anything. Because the way that you can think about it is in that wide data structure, if there's a hole anywhere, it can't figure out what the sums of squares is going to be for that person, and it can't be used. The same rule is true in these analyses. The row has to be complete in order for that piece of information to enter into your analysis. We are changing our definition of what a row is. In this long stacked data structure, a row is an outcome per person. So any of these rows that is incomplete with respect to either a predictor or an outcome does not get included. That means it's not listwise deletion, but it's partial deletion if you're missing some of the story for a particular outcome. The assumption that we're making in using likelihood estimation is something known as missing at random, which is confusing because it's not what it sounds like. So in terms of missing data, there's a classic categorization scheme that people have largely agreed on and used the same words for. There's missing completely at random, missing at random, and missing not at random. Completely at random is exactly what it sounds like. Like there's no reason why you're missing the data, and it's completely unrelated to what the people would have said. You are assuming missing completely at random when you do listwise deletion via least squares, because it doesn't know what data used to be there, like the whole thing is just gone. This is a less strict assumption. Missing at random means it's random conditional on the information that we do have about a person. So in terms of my likelihood mountain, right, I have my height in multiple dimensions. The assumption is essentially that the same shape would hold for that person even if we didn't have all the outcomes creating that shape. So if I know what their pretest score was, conditional on that knowledge, then the outcome being missing would be missing at random. So it's taking into account the information you do have in order to make a better prediction. Anything that uses likelihood estimation or multiple imputation, this is an assumption that's baked in, missing at random. Unfortunately, it's not testable. Unlike most things in statistics where it's like, well, do you need this? Let's find out. This is an empirical question. You don't have the data to find out. So reviewer 2 loves to ask you about missing at random and whether that's plausible for your data, because reviewer 2 knows that you can't answer that question. So it's important, I think, in touting the benefits of switching to a different way of estimating that you could, to keep more incomplete cases, you can keep whatever is complete, but not drop the whole person. It comes at a cost in terms of the type of assumption that has to be true for this to be valid. Whole people are going to be removed if they are missing a predictor that is measured per person. So let's say that you collected a baseline value, someone's score, a personality measure, or something like that, and you didn't give it to them at every occasion in a longitudinal study. If you enter that variable as a predictor in your model, then it would be missing for all the rows for the same person, and they're gone. So this idea that you're addressing missing data via likelihood estimation does not hold for person-level predictors. Then you're back to missing completely at random listwise deletion for those. The alternative would be multiple imputation, which is filling in missing values based on the rest of the information that you have, but not filling in the direct prediction, adding an error to it so it's not cheating. Anything that you see that allows you to do single value imputation, like in SPSS, there's a box you can check that says, hey, would you like to plug in the mean for all your missing values or plug in a regression prediction? Never check that box. Never. You are not allowed to fill in the holes of missing data. You're allowed to fill in the holes of missing data if you do it repeatedly and you add an error term each time, and then you analyze every single completed data set and compile the results back together. That's multiple imputation. That sounds like a big pain in the butt, but modern software has ways to do this for you behind the scenes. So never fill in the holes with single values. That's the take home here. So because these are advanced topics that are important, but I can't get into all of the nuances, and no, there's not a class on this, and yes, there should be, we're going to follow the practice of pre-selecting our sample to be complete with respect to all the columns. That way the sample stays consistent across all of the analyses. As a shout out, so earlier this semester, APA has a new series of free trainings that they're doing where you can log in and like watch famous people talk about this stuff. I'm not famous, but they let me do it anyway. But someone who is famous about missing data is Craig Enders. He has a very good textbook that just came out with the second edition, and he's giving a talk about missing data in this series later this month. So I would recommend checking that out. At least the hour-long talk will give you an introduction, and he is an excellent writer, very clear communicator, and so I think if you're interested in learning about sort of state-of-the-art ways to address missing data, that's who I would go to. He's at UCLA in quantitative psychology, and he grew up in Nebraska with me. Not like with me, he's like older than me, but we went through the same pathway at the University of Nebraska-Lincoln. So, and he worked there as well before my time. Anyway, so a little bit of sad news, but I feel it's important to be upfront. Questions or comments on any of that? No. Did that make you too sad? No, because this is a thing, like you'll read it in papers. Oh, we handled missing data. We handled it with multiple imputation, or we handled it with likelihood, maximum likelihood. When people say handle, it means they don't know what they're talking about. It's a hand-wavy sort of term. So the deal is complete rows get included in the analysis, but the definition of a row has changed to be per outcome rather than per person. So what if I have 2 people and 3 outcomes? Same idea, just the shape of the block diagonal would change. So if I have 3 different outcomes, then potentially I would have 2 predictors to differentiate among the 3 outcomes. So the same concept, like when you put a grouping variable, like a categorical predictor into your model, let's say that you have 4 groups, how many slopes do you need to put in to differentiate 4 groups? If I got 4 groups, how many slopes do I need to put in my model to fully differentiate them? 3? I can't see your fingers, I'm too blind. 3? Is that your vote? That's your vote. What are you voting for? 3? Erica, 3? Anyone else want to dissent? We're all in agreement? It is 3. Yes, because you have the intercept. That's why. So the intercept is the outcome for one of the groups, and then you have like the offness relative for each of the others. Same idea here. If I have 3 potential outcomes, then I have beta 0 as like my reference outcome, whichever one I decide that's going to be. And then I'd need a predictor to differentiate the first outcome from the reference and the second outcome from the reference. So it's the same set of concepts, just on the outcome side rather than the predictor side, because from the perspective of the analysis, they are predictors. I have one outcome, it's called Y, but secretly I have 3 because I can include which is which as predictor variables here. So now I have a residual variance for my first outcome, my second outcome, and my third outcome. Those could be the same number, or they could be different numbers. That's an empirical question. Likewise, I have a covariance between my first and second, my first and third, and my second and third. Those could be the same, or they could be different. Another empirical question. The good news is that you've already learned how to answer that empirical question. Any guesses as to how we would figure out, like, if these need to be the same or different? Not this time. How did we determine if we needed, like, a stretchy factor in our count model, or a stretchy factor in our binomial model? You just did this in the homework. Yes, but test what? The model fit? Like, what's the number that goes in? You're right. I'm just trying to get the vocabulary. The deviance test. And what's the number that goes into the test? That's one of them. What's another one? What's the first number I ask you for every single model to make sure your model's right? -2 log likelihood. The height. And actually, log likelihood is height. If you multiply that by -2, that's shortness. So it changes the inference. In height, bigger is better. In shortness, smaller is better. Yeah, that's the exact same thing. We're going to look at how tall is the set of 3 observations if I make all the residual variances the same, and then how much shorter would it be if I constrained them, or actually, let me say it the other way. If I let them be whatever they want, does it make the height significantly shorter to force them to be equal? Or if I start with them equal, does it make the height significantly better, taller, to let them be different? In general, in quantitative methods, anytime you have a question about what kind of variance something you have, whether you need a stretchy factor, whether you need multiple residual variances, or whether they can share one, whether these covariances are different than 0, all of that is answerable via comparisons of -2 log likelihood. That is a universal thing. The same thing will be true if you take structural equation modeling with me or factor analysis with me. The extent to which the model that you fit is consistent with the data is a likelihood ratio test. They show up in everything. So that's one of the reasons why I wanted to incorporate that into this course, so that you have that as a toolkit to apply to all your other coursework. So now we have choices about whether these variances should be the same across outcomes or whether they should be different. So what are the choices then? In likelihood-based estimation, there are a whole bunch of choices. In the context of sort of generic multivariate data, so different outcomes, there's really only a couple that would be relevant. There are many, many more choices that would potentially be relevant for longitudinal data specifically. Also, spatial data specifically. Does anyone work with, like, census data, where you would have observations that are close with respect to, like, space and time, like EEG data or like fMRI data, that kind of stuff? There are spatial covariant structures as well that are possible. But in the context of, like, I have dependent variable A, B, and C, like something generic, there's only a few that you would see. So if we're in the world of general linear model, continue-ish outcomes, not generalized, but the world of, like, regression, ANOVA, that kind of thing, then we have directly ability to add covariances into this R matrix. So here's what the code would look like within SAS, within Stata, and within R. And I've got examples of these to show you, where we would tell it what the indicator variable is that keeps track of which outcome is which. So I have this labeled here generically as DV index, which stands for dependent variable index. So is this outcome 1, outcome 2, or outcome 3? Then you tell it this type right here is where you would tell it what type of pattern you want. Do you want all the variances to be the same, or do you want them to be different? Do you want the covariances to be the same? Do you want them to be 0, or do you want them to be different? Those are your basic types of choices. So here is the right answer always as a point of comparison. The word for this varies depending on which class I'm teaching. Today, it is unstructured. In structural equation modeling, this same concept is called the saturated model. Both of those words are meant to convey the idea that everything within this little block diagonal gets to be whatever it wants. So I'm going to let the first outcome have it's whatever residual variance the data want it to have, the second outcome and the third outcome, all separate. Likewise, each pairwise covariance, all separate. So if I have 3 outcomes, how many different things am I trying to estimate? And by thing, I mean parameter. How many unique different things are in this matrix right here? It's symmetric, so not all of them count. I'll help you count. How many variances on the diagonal? 3. Yeah, it's not meant to be a trick question. It's Thursday, 4 weeks before the end of the semester. There will be no trick questions. Just going for shameless audience participation as usual. So yeah, 3 things on the diagonal. How many unique things do you see on the off diagonals? 3 also, because 1, 2, and 1, 2 are the same. So you usually only count either the top section or the bottom section. So that's 6 things if I have 3 outcomes. What if I had 4 outcomes? I'd have 4 variances. How many possible pairs of covariances would I have for 4? Not quite. This is like n choose 2 or something. There's a formula for it, but I can just do it on my fingers. 1 with 2, 1 with 3, 1 with 4. Let's see, 2 with 3, 2 with 4, 3 with 4. 6. So if I have 4 outcomes, now I'm up to 10. What if I have 5 outcomes? 15. So this is great when you only have maybe 2 or 3 different outcomes. You can easily let them all be whatever they want, but this becomes untenable when you have a lot of outcomes. The good news is that this will always fit the best because there's no constraints on this. Like you're letting everything just be whatever it wants. The extent to which a simpler version is adequate is an empirical question, answerable via a likelihood ratio test. So here's the formula by which you can figure out how many unique spots there are in this R matrix. Number of outcomes times number of outcomes plus 1 divided by 2. If you're familiar with structural equation modeling, this equation will look like how you calculate degrees of freedom for your structural equation model based on the number of variables, and that is not a coincidence. That is exactly what I'm talking about. So R is a covariance matrix in notation. So these are variances and covariances, but I can convert it into correlations by taking the covariance and divided by the standard deviation of each of the 2 variables here. So in your output, you will get both forms of these printed for you so that you can literally see how correlated the residuals are from the same person. That's a parameter that gets estimated. The extent to which these off-diagonal correlations are different than 0 is essentially your effect size for how much dependency you have to worry about. If they're not different than 0, then functionally speaking, you have an independent sample. So this will always fit the best, but it becomes untenable if you have a lot of outcomes. So we look for compromises that would be reasonable. This same idea of unstructured in this class, it's unstructured in my longitudinal class, it's saturated in the structural equation models class, and if you take multivariate, you will know this as MANOVA. So this is the MANOVA multivariate approach to repeated measures ANOVA. The only difference is that when people use those words, they're talking about least squares estimation rather than likelihood. The difference would be whether or not you get to keep in incomplete cases. So this idea of starting with like a baseline of like, just let everything be what it wants, that's your best choice, shows up in a lot of different contexts. Here's an alternative that is not readily available in all software, but I want you to have heard of it. This is a pattern that is called compound symmetry heterogeneous. This pattern says, okay, yep, all 3 residual variances across my 3 outcomes, for example, get to be different. But the covariance across each pair is built with a common ingredient labeled CSH here. That's a correlation. So broadly speaking, what this option says is let the residual variance be whatever it wants for each of my separate outcomes, but constrain the correlations to all be equal to each other. So outcome 1 is just as related to outcome 2 as it is to outcome 3, and outcome 2 is just as related to outcome 3. Then there's one more that puts a constraint on the variances too. So this is called compound symmetry. This is an ANOVA term. What it means is that we are saying that all the residual variances across outcomes are the same, and therefore all of the correlations and covariances across outcomes are the same as well. So Gonzalo, you had asked me about sphericity. Like, this is the univariate approach to repeated measures ANOVA. That's what this is. And in order for that to be reasonable, the constraint is not this one. It is that the difference between these outcomes, between each pair, has the same variance, and the difference between outcomes has the same covariance. So it's a little bit less restrictive than this, but this is what most people have when they talk about univariate repeated measures ANOVA. The idea of controlling for individual differences and kicking that out of the error term, CS is the name of the thing you're kicking out of the error term. So you're saying that the reason that people have variability in this outcome is in part what is common. So like if these are, let's say, 3 different speeded tasks, maybe I'm just faster than everybody else. And so that's part of the reason for my variability across people, is that there's something in common. And then there's something left over that's not in common. And that's the residual variance here. So it's splitting this into what is common to me and unique to the outcome in this case. So these choices are only possible to do in this way if you're in the general linear models world, because we have to have the capacity to separately estimate a residual variance in order to have correlations and covariances between them. But the same idea of what is in common, let's let that sort of operate across all the outcomes and then see what's left over, is the basis of random effects models. A random effect is this common thing, the CS thing. It is a semantic distinction. So how do we decide which one we would like best? Likelihood ratio tests. So your choices then, adding another baseline would be independent, meaning there's no dependency. So if you do a likelihood ratio test for a model where you have no residual correlation versus constant correlation and constant variance, that means you have dependency. If you add the idea of heterogeneous variances, that means that you have different outcome variances based on which outcome it is. And if you fit unstructured, which is then letting all the covariances be whatever they want and that fits better, that means you have different patterns of residual correlation based on which outcome it is. So all of these things are all nested within each other. Tallest wins for log likelihood, smallest wins for -2 log likelihood, AIC and BIC. So the goal is to find a model that fits not worse than unstructured. So the way that I would talk about it is with that language. Like, the purpose of the likelihood ratio test would be to see if I can come up with something that's simpler but does as good a job. Not worse than perfect, not worse than unstructured. All right. Yeah. I don't know if I want to go into this. Yeah, okay, maybe one more thing. One more, do we have energy for one more thing? I think. Okay, one more thing. So the idea of how you add stuff to a model and see if it helps. That is a concept, right? The process for doing that depends on the kind of thing you're adding. If you're talking about fixed effects, or what I refer to more generally as the model for the means. Like, how do we create a predicted outcome for each person? What predictor variables do we need? Do they only need main effects or do they need interactions? Do they have linear slopes or nonlinear slopes? Like all those choices, right? You can decide what goes into your model in terms of a predictor. You can always do univariate or multivariate walled tests. And you're like, do I know how to do that? Yes, you do. Do you know, like, when you get your output and it has your slope and your standard error and then like a test statistic and a p-value? That's univariate walled test. So you know how to do that because you can just stare at the p-values that show up in your output. Cool. If you are using denominator degrees of freedom, some people would say you can't say walled for that anymore as a name, but I'd say, it's a walled test with degrees of freedom, whatever. Multivariate walled test is the idea of lumping slopes together. You've done that too. So let's say that I have an interaction that requires two different slopes, such as the effect of food school, right? So food school in my last homework was a binary predictor and the number of sessions. In order to talk about the effectiveness of food school, I have to lump those two slopes together to get like an omnibus test. That's a multivariate walled test. It's an F if you're using denominator degrees of freedom. It's a chi-square if you're not. So no matter what kind of model you're fitting, whether it's a general model, a generalized model, a multi-level model, a structural equation model, any other kind of model, a survival analysis, like any other thing in the world, you can do this. If you are using residual maximum likelihood, that's your only choice. If you're using regular maximum likelihood, which is what we've been doing throughout the semester, we could also do likelihood ratio tests for this. And in a few spots during this class, I've had us add predictors and do likelihood ratio tests. The reason that I did that was because I got different answers out of R if I did it the other way. That was literally the only reason. So you can do likelihood ratio tests for this, but you don't have to. You can stare at the p-values that show up on your output otherwise. In contrast, if you're making decisions about the model for the variance, so what kind of distribution you need, whether if you have separate variances across outcomes, whether they need to be the same number or whether they can be different numbers, do you have residual correlation across the outcomes from the same person? Does that depend on which outcome it is? All of those sorts of choices, you have to do likelihood ratio tests. We can't do walled tests because variances don't have a normal sampling distribution. And it gets less normal the closer that thing gets to zero. So any sort of decision that we make about variance or stretchiness or over dispersion or residual correlation or dependency, all of that is some kind of likelihood ratio test. So here's some examples of when we've seen that. Adding zero inflation, like that's a likelihood ratio test to see if we need that. All right, yeah, that's enough. No more matrices this week. I don't have the strength for that. You know what I'm saying? Yeah, so. And if you're like, oh my God, this is so much, yes, you're not wrong. My objective is to show it to you, to get you at least like having seen it, and then if you continue in the coursework, we dive deeper and we do a lot more practice with this. All right, questions or comments? No more matrices today. So big picture, everything that we do with respect to predictors is going to look the same. All of the decisions about multivariate refer to the pattern of correlation of your residuals and whether or not each outcome would need a different residual variance or a different stretchy factor or whatever type of variance model parameter you're dealing with. That's the new part. All right, 308. I'm calling it a day, a week. Any questions before we call it a week? Or things you want me to go back over? Questions? Yes? So you're asking about the idea of a mixture chi-square distribution that your difference in -2 log likelihood is referred to. The rationale is that sometimes the thing that you're adding has a null hypothesis of 0, like that's this, but that's also the smallest it could be. So there's a term for that. It's known as when you're on the boundary of the sample space for that parameter. And like if you wanted to add, say, a variance to your model, or let's do a stretchy factor, you know that one. Okay. So if you don't need the stretchy factor, like it will be close to 0 and it won't help. But stretchy factors can't go negative. So the idea of like, what would the distribution of my stretchy look like if 0 were the center? Some of it would have to be negative stretchies, and that can't be a thing. So this mixture chi-square uses a 0 for like the weight for the side it can't get to because it doesn't exist, and a 1 for the rest of it. And so what it amounts to if you're only adding one stretchy is that you can pretend like it's a one-tailed test because like literally the negative side is not available to you. But the same problem shows up in different contexts. Anytime that you're adding something where the lowest it can be is 0, but that's also the null hypothesis, that would imply there's a negative possibility. So, cool? Okay, all right. And if you forget about this and you're like, what the hell is she talking about? I'm just going to do a likelihood ratio test. You're being a scotch conservative. That's what the difference would be. So like the critical value for adding one thing is 3.84 in a regular chi-square, and it's 2.71 in a mixture. So there's very few situations in which you'd be in between in which someone cares. So if you're like, I'm just going to ignore it and not care and be a little conservative, I'm with you. But in case reviewer 3 it yells at you about this, I wanted you to have seen it. All right. Then let me know if you need anything. Let's see. Formative assessment is due Monday. Have good weekends. And no office hours for Vladimir tomorrow. He is at a conference. So you're stuck with me until next week. Office hours are Mondays and Wednesdays from 12 to 1:30 over Zoom. First come, first serve. So I try to answer questions in the order in which people appeared, and you're welcome to show up at any point in that hour and a half. All right, thanks folks. Catch you on the other side. Bye, Zoomers.